Welcome to this lesson on dimensional analysis and the atomic bomb. This screencast really just builds on the ideas that you learned in a previous screencast about dimensional analysis, and this is just to show you an amazing historical example of how dimensional analysis got used. So here's the amazing piece of history. The United States, as you might know, first detonated an atomic bomb in 1945. This was called the Trinity Test. It was an atomic bomb test performed at White Sands, New Mexico. And for reasons that aren't hard to imagine relating to national security, a lot of things about this test were, sort of highly classified secrets. People didn't know, the public didn't know very much about this. However, there was this physicist named G.I. Taylor, that's this guy here, and he used dimensional analysis and photographs, which I'll show you in a minute, and a little bit of extra information, but essentially dimensional analysis and photographs in order to figure out the explosive energy of the atomic bomb, which was supposed to be a closely guarded secret. And this really freaked people out that this guy was able to figure it out using math and pictures. And I want to walk you through how he did it. One thing you need to understand is what kind of data he had available. And one thing that was available to some observers, or to some members of the community, were pictures of the blast. So what you're seeing here are actual pictures of the blast front, and it's spreading out, right? So you can see there's this bar that says 100 meters. So you can see that in this series of pictures, it's getting bigger, and you can see that there's a timestamp on each picture. So this thing kind of looks sort of like a sphere, or part of a sphere, and it gets bigger as time goes on. And so this results in a data set that looks something like this. For each value of time, what was the blast radius at that time? Basically, how big was this kind of mushroom cloud sort of thing? And I'm showing you the first four values here, but there were a number of other data points available as well. And that's what G.I. Taylor had available to him just from photos that were published in various places. So the way he started this problem was just to use dimensional analysis to figure out what is the radius r of the blast front. So he started out not trying to write down an expression for the energy, which is eventually what he figured out, but an expression for the radius. And so step one in dimensional analysis, identify the relevant quantities. They're going to be the radius of the blast front. Well, we know it depends on time. Because he was a physicist, he also knew it should depend on air density and definitely on the explosive energy of the bomb, which in the end is going to be the thing we're going to figure out. But we're going to start out trying to predict the radius of the blast front. Okay? And so in step two, when we ask what are the dependent and independent variables, we'll think of that radius as being the dependent variable, and it depends on time, air density, and the explosive energy of the bomb. Next step in dimensional analysis is to list the dimensions of all those quantities. Well, the radius is like a distance or a length, so it has dimensions L. Time has dimensions capital T. Density of air, density means mass per volume, so that's ml to the minus 3. And energy is like a force times a displacement, and force is mass times acceleration. So that's mlt to the minus 2 times an extra factor of L, so you get ml squared t to the minus 2 for energy. Okay, step 4 is to write the dependent variable proportional to a generalized product of the independent ones, just like you've done before. So radius is a dimensionless constant times t to the a, rho to the b, e to the c, where the exponents a, b, and c are the things that you are going to try to determine. And this is what G.I. Taylor did. And so I've repeated steps 3 and 4 for you here for convenience. The new step is step 5, where we write the dimensional version of the equation. So r, as we know, has dimensions L, k carries no dimensions, t to the a gives us capital T to the a, rho to the b gives us m L to the minus 3, all to the b power, and e to the c gives us ml squared t to the minus 2, all to the c power. And then we can combine the l's, the t's, and the m's. We get this expression here. The next step is to actually invoke dimensional compatibility, right? The dimensions of what's on the left have to equal the dimensions of what's on the right. And so we do that for each of L, T, and M. So if we look at L, there's 1 power of L on the left, and on the right there's minus 3b plus 2c. There's no powers of T over here, so 0 on the left. On the right we have a minus 2c. And for mass, we have 0 powers of m on the left, and on the right we have b plus c. So we get this system. This is 3 equations and 3 unknowns. They're linear equations. You can solve them using your favorite method. You find these values here. A equals 2/5, B is minus 1/5, and C is 1/5. Okay, so now we take those and we substitute them to get a final answer for R. So since this was our generalized expression for R, and since we had these values of A, B, and C, we put it all together to get R is K T to the 2/5, rho to the minus 1/5, E to the 1/5. We can remember what positive and negative powers mean if we want, and write this as K times ET squared over rho, all to the 1/5 power. Okay, now, here's what G.I. Taylor did at this point. So one thing is that rho equals 1 is a well-known property, the density of air. Okay, so in the system of units that he was using, rho is approximately equal to 1. Also, this is a little bit beyond the scope of dimensional analysis and beyond the scope of something that you can work out easily. So I'll wave my hands a little bit here, but G.I. Taylor was able to figure out, using physics, that the value of K should be approximately 1. So if we're willing to use G.I. Taylor's bit of physics, and if we're willing to look up the value of air density, we can plug in 1 for K and rho, and we get something like R equals ET squared to the 1/5 power. Okay, that's an expression that comes from dimensional analysis and this little bit of extra information. Now don't forget to say wow at this point. We're not done with the problem, but the fact that you were able to figure out how the blast radius depends on energy and time is, I think, pretty amazing. Now what we have to do is actually use our data to figure out the value of E. So we started out with this expression here. This is what came from dimensional analysis, and you might remember that this is basically a power rule. We have variables multiplied together raised to powers. And sometimes a good way to fit data to a power rule is to take the log of each side. So we're going to take natural log of each side. On the left, I just get ln r. On the right, if you want to see how this works out, it's ln of et squared, that whole thing, to the 1/5 power. But that's equal to the natural log of e to the 1/5 t to the 2/5. And you can remember the rule of natural logs, that the log of a product is the sum of the logs. So that's the natural log of e to the 1/5 plus natural log of t to the 2/5. And then you can remember that for logs, you're allowed to bring these exponents down in front. Okay, and that's what will lead you to this expression on the right-hand side here. 2/5 ln t plus 1/5 ln e. Okay, so then the way you should think about this is that r is a dependent variable, t is like an independent variable in your data set that you have, r versus t, and e is what you're trying to figure out. You think of this as your y variable, you think of this as your x variable, and you think of this whole thing as a y-intercept. So it's like this equation says y equals 2/5 x plus b. Now you take all your data, the data that G.I. Taylor gathered from pictures, where he had values of t and r, and he plots a bunch of ordered pairs. So for every data point, he takes the natural log of time and the natural log of r, and he plots it in a graph that looks something like this, and you get a whole series of points. And then the question you can ask is, well, we know that if we plot ln r versus ln t, we should get a line with slope 2/5. So we can ask which line with slope 2/5 best fits this data, and you can use computer software to do it. It turns out to be this line here, which has a y-intercept of 6.371. Okay, the next thing to do is simply to equate that y-intercept, 6.371, with the y-intercept from our kind of model equation here, right? So you say 1/5 ln e, that's the y-intercept in our equation. Well, that must equal the y-intercept that fits our data, 6.371. So you multiply by 5, you exponentiate, and you find the value of E. Turns out to be about 6.8 times 10 to the 13th joules. That was approximately what G.I. Taylor guessed using these methods. The actual value of the explosive power of the bomb was about 9 times 10 to the 13th joules. You should notice that those are both times 10 to the 13th. This one is about 7, this one is about 9, so there's some error there. But he was really in the ballpark with his guess without knowing very much about the secrets of the bomb. And that's what really freaked people out, is that he was able to deduce the information. So that's the end of what I think is really a pretty amazing historical tidbit.